Hello and welcome to the ARSET training, Application of NASA's SPoRT Land Information System Soil Moisture Data for Drought. My name is Sean McCartney and I'm an ARSET trainer based at NASA's Goddard Space Flight Center in Greenbelt, Maryland. It's a pleasure to welcome you all to the first part of this three-part webinar series. For those unfamiliar with the Applied Remote Sensing Training Program, or ARSET, ARSET is part of NASA's Applied Sciences Capacity Building Program. ARSET provides accessible, relevant, and cost-free training on remote sensing satellites, sensors, methods, tools, and applications. Trainings include a variety of applications of satellite data and are tailored to audiences with a variety of experience levels, from introductory to advanced. On the right of the slide, we see the 6 application areas in which ARSET conducts our trainings, including agriculture, climate and resilience, disasters, ecological conservation, health and air quality, and water resources. Trainings are conducted both online and in person and are offered live and instructor-led, or asynchronous and self-paced. All ARSET trainings are offered cost-free and include bilingual and multilingual options. Only publicly available data and open source and open access software is used in our trainings. We accommodate different levels of expertise with our trainings, ranging from introductory to advanced. We encourage you to visit our website to learn more about the ARSET program and sign up on our listserv to receive email updates on upcoming trainings. The following slides will provide an overview of the training, Application of NASA's SPoRT Land Information System Soil Moisture Data for Drought. According to the World Health Organization, an estimated 55 million people globally are affected by droughts every year. Traditional drought applications and indices focus on sensible weather and precipitation trends and their impacts on the hydrologic system. This training is focused on the introduction of the NASA Land Information System, or LIS, output of soil moisture at various depths for drought analysis and monitoring. LIS output of soil moisture will enable a more efficient drought analysis via a gridded product as opposed to sparse in situ measurements of weather parameters and even less dense soil moisture and vegetation health in situ observations. The spatial tracking and analysis of soil moisture by LIS provides a unique tool for those monitoring drought locally compared to large-scale traditional indices forced by weather factors. After participating in this 3-part training, a user will be able to apply LIS output to efficiently analyze drought over large spatial areas in conjunction with current practices and to integrate the capability with existing data. You will be able to identify the NASA LIS basics regarding the framework, input forcing, static fields, land surface modeling structure, and output most relevant to drought. You'll be able to summarize the derived soil moisture percentile products and how these are created. You'll also be able to apply SPoRT-LIS output and/or derived products to both complement existing data and overcome limitations to monitoring drought over large areas. You'll be able to recognize best practices for LIS impact related to drought. And finally, after participating in this 3-part training, you'll be able to configure LIS output file for viewing within a GIS-based display tool and for tailored output products and graphics. The prerequisites for this 3-part training are ARSET's Fundamentals of Remote Sensing Session 1. You should download and install QGIS and all accompanying software. You'll need to register for a Google Colab via Gmail or a Gmail-enabled account. And though basic Python experience is beneficial, it is not required to be able to run the Google Colab notebooks that you'll be using. This slide provides the training outline for this three-part webinar series. Over these 3 weeks, there will be 3 1.5-hour sessions, which will include presentations, demonstrations, as well as question and answer sessions. All materials and recordings from each session are available on the training webpage. Part 1 is focused on a foundational understanding of LIS, the static forcing models and output. Following each session, there will be a self-paced micro lesson, which will not be graded, but will serve as a knowledge check and prepare you for the following parts of the webinar series, as well as prepare you for the final homework assignment. There will be one homework assignment, which will be posted on May 31st on the ARSET training page, and there will be a due date for that one homework assignment on June 14th. A certificate of completion will be awarded to those who attend all live sessions and complete the homework assignment before the given due date. Listed below are the trainers for today's webinar. Chris Hain is a physical research scientist at NASA's Marshall Space Flight Center, as well as a project lead for NASA's Short-Term Prediction Center and Transition Center, or SPoRT. Sujay Kumar is a research physical scientist in the Hydrological Sciences Lab at NASA's Goddard Space Flight Center. And Jonathan Case is a research meteorologist with NASA SPoRT at NASA's Marshall Space Flight Center. The objective for today in this first part of the webinar series are as follows. By the end of part 1, participants will be able to identify the NASA LIS basics regarding the framework, input forcing, static fields, land surface modeling structure, and output most relevant to drought. You'll also be able to summarize the derived soil moisture percentile products and how these are created. Questions are encouraged. If you have any questions, please put them in the questions box and we will address them at the end of the webinar in the order that they were received. Feel free to enter your questions as we go. We will try to get to all of the questions during the question and answer session after the presentations of this webinar have concluded. The remainder of the questions that we don't get to will be answered in the question and answer document, and we will post them to the training website about a week after the training. We will now transition to Dr. Chris Hain to introduce SPoRT-LIS for drought training. Chris, over to you.
Thank you. My name is Christopher Hain, and I am the project lead for the NASA SPoRT, the Short-Term Prediction Research and Transition Center. I wanted to welcome you to the first session of ARSET's application of NASA's SPoRT's Land Information System Soil Moisture Data for Drought Training. We have an excellent set of presentations and tutorials over the next 3 weeks that I'm sure will leave you with a better appreciation for the use of land surface modeling for the monitoring of drought. Over the past 2 decades, SPoRT has pioneered a paradigm focused on improving the research to operations process. SPoRT was started to address something we call the Valley of Death, where a gap existed between scientists and decision makers, which caused inefficiencies in the process of getting cutting-edge research into the hands of people who needed to make important decisions. To address this challenge, SPoRT's unique research to operations process starts with the decision maker. We bring the decision maker into the process at the beginning to learn and understand what their needs and challenges are. So when we say decision maker, who are we actually talking about? Some of the groups that we've worked with actively over the last 2 decades have included NOAA and the National Weather Service, which really started out as our primary stakeholders in the operational weather community. And then over the last number of years, we really worked to broaden out our reach to additional decision-making groups that can benefit both from NASA products and modeling capabilities. Within our process, after we identify a group that we aim to work with, the first part of our research to operations paradigm is to learn about their decision-making process and to identify forecast challenges that exist. So at this point, once we identify a challenge, we can go back to the scientific community and find or develop a solution that we can then introduce to our decision maker. After we identify that solution to a known forecast challenge, we can start the process of getting that new product or capability in front of the decision maker. Usually the product or capability may be new to the decision maker, so our team works to develop training tools to help the users become acclimated to the new product or capability. One example of training tools are the development of virtual class type material, which allows the decision maker to learn about how the product was developed and examples of how it can be used to address their specific forecast challenge. At times, a decision maker needs a shorter format piece of training that can be quickly referenced while in a decision-making process. Therefore, for all our new products and capabilities, we also develop something we call quick guides, which are a 1 to 2 page overview of the product, which provides the most relevant information that can be quickly assessed by the decision maker while they're making a decision within their process. At this point, we've integrated the new product or capability into the decision-making process and provided training for its use. The next step in our process is to do a targeted assessment period where we can observe how the decision maker is using the product and get feedback from them on the potential improvements or changes to the product or capability that could be made. After the assessment period ends, we meet with the decision maker and together determine if the forecast challenge has been properly addressed by the introduction of this new product or capability, or if further development is needed. So at this point, we kind of reach a fork in the road where we have to determine what success is, with 2 potential outcomes. Success is we finish the process and the decision maker takes ownership of the new product or capability and integrates it into their long-term solution within their decision-making process. But often we find issues, new challenges, or ways that the product can be improved. Therefore, we go back through a process we call operations to research, where feedback from the research to operations process helps motivate improvements or changes to the product or capability. And we stay within this iterative loop until the decision maker is happy with the new product and capability, and we can exit our process and integrate that into their operational decision-making process. So the tool that we're going to be showing over the next couple of weeks is really one that we developed for the drought monitoring community, and one that the drought monitoring community has been using for a number of years to make and improve their decision-making process when it comes to both drought monitoring and prediction. While our initial focus with our research to operations paradigm was the operational weather community, and working on activities with both NOAA and the National Weather Service, over the past 5 years, we've broadened our approach used within SPoRT to address forecast challenges in other scientific communities. These areas include wildfire monitoring, disaster response, agriculture, water management, and air quality and human health. And as I said before, another community where our activities have expanded is within drought monitoring and prediction, and one you'll learn a lot about today and in subsequent periods. And that serves as the main motivation for this training, to show how the combination of land surface modeling and remote sensing can be used to provide important information about the land surface state, states like soil moisture, which are heavily affected by drought, and variables that can be used to help better specify drought. Before we get into the main program today, I wanted to finish with one visual example of how far the drought monitoring community has come in the past 23 years. Back in the year 2000, the United States Drought Monitor started producing weekly maps of the drought extent across the United States. As you can see there on the left, this map from May 2nd, 2000 looks familiar and shows the spatial extent of drought conditions on that day. One thing that jumps out to me is that the effective spatial resolution of these drought classifications are on the order of hundreds of kilometers. The lines tend to be very smooth. There isn't a lot of detail in the map shown there. And this was because the inputs that were used to draw these maps were relatively coarse, and there wasn't a lot of high resolution products and capabilities that were able to classify drought and provide finer scale resolution for the authors to actually make more detailed assessments of the current drought extent. Fast forward to the same day this year. This map is from May 2nd, 2023. This map shows the US Drought Monitor shows details on the scales of tens of kilometers at times. For example, look at the spatial detail over Texas in 2023 compared to the spatial detail from 2000. These improvements have been realized because of the innovation and development of high resolution products that allow the US Drought Monitor authors to get down to the spatial detail that you see in the maps today. One of these products is the reason we are here today. High-resolution land surface modeling frameworks, such as the one employed in our SPoRT-LIS system, have helped move the drought community forward, and we're here today to show the community a bit more detail on how we employ our system for drought monitoring. So I will close my introduction with a reminder that the SPoRT mission is to develop scientific solutions based on stakeholder feedback. And while you're here today to learn from us, we'd like to hear from you too. Below is our contact information, and we welcome any comments, suggestions, or just examples of how you use data in our work. With that, I'd like to thank you for taking time out of your schedule to attend this training, and I hope you enjoy the sessions.
Thank you, Chris, for the terrific introduction to SPoRT-LIS. We will now go to Dr. Sujay Kumar to provide an overview of NASA Land Information System Framework and outputs. Sujay, over to you.
Hello, everyone. My name is Sujay Kumar. I'm a research physical scientist in the Hydrological Sciences Lab at NASA's Goddard Space Flight Center. I focus on studying the terrestrial water cycle with models and remote sensing. I'm also the lead for the NASA Land Information System, or the LIS project. Today, I'm happy to provide an overview of the LIS system and how LIS enables the drought characterization by combining state-of-the-art modeling and remote sensing. So what exactly is the land information system? At a high level, it's a system designed for coupled and uncoupled land surface modeling and data assimilation. The schematic on the right here represents the water cycle, and the area marked by the black line represents the terrestrial leg of the global water cycle. In an uncoupled setup, LIS primarily focuses on the processes of the terrestrial water cycle, the processes through which precipitation that falls on the land surface separates into different components of evaporation, runoff, and storage terms of soil moisture, snow, etc. So now data assimilation is the mathematical approach to incorporating information from observations within our models. So the overall philosophy of land data assimilation systems, such as LIS, is to use the best available observations to force and constrain our model estimates. So there are numerous applications to the outputs produced by LIS. It ranges from initializing weather and climate models, water resources management applications, monitoring of hazards and the associated management, among others. So here's a bit of history about LIS. The project started in 2002, evolving from two existing projects called the North American Land Data Assimilation System, or NLDAS, and the Global Land Data Assimilation System called GLDAS. So the NLDAS environment covered the continental US at 1/8 degree spatial resolution, whereas the GLDAS environment encompassed a global domain at 1/4 degree spatial resolution. So these two systems had very specific configurations and were not flexible for other regions and configuration. So when we started the LIS project, we had a number of key requirements. The first one was obviously to have a system that's flexible enough to be used at different spatial resolutions and different spatial extents. We also needed a system that's able to represent the land surface processes at the same spatial scale as that of clouds and precipitation processes to accurately characterize land atmosphere interaction. So as we go to fine spatial resolution, it obviously means that the computational needs grow significantly, and therefore we need to build the high performance computing support for these simulations, which the existing NLDAS and GLDAS systems lacked at that time. So more importantly, we needed the ability to incorporate remote sensing information as constraints to modeling through methods like data assimilation and inverse modeling. So we developed a fairly comprehensive environment in the last 20 years that accomplished all of these requirements. So here's a schematic that shows the timeline of the LIS project. which, like I said, started in 2002 as a NASA-funded computational technology project. And over the years, the LIS system has evolved into a state-of-the-art land surface and hydrology modeling system with a variety of capabilities for remote sensing data infusion. And consequently, LIS is used by several agencies around the world, many for drought monitoring. So for example, the LIS-based environment is used by USAID and NASA SPoRT to develop drought characterization and to assist with food security relevant applications. So this slide here shows the extent of the LIS use at NASA, from the development of missions all the way to end use applications. So we use LIS capabilities to develop assessments of the potential utility of hydrological measurements from future space missions. So these studies have been conducted during the mission development of missions such as GPM, Aquarius, and SMAP. For active missions, we obviously use the LIS capabilities to demonstrate the utility of remote sensing data sets for water cycle studies. And finally, there are a ton of hydrology applications where LIS is used, ranging from numerical weather prediction to water security assessment to food security and quantification of extremes. So as I said before, there are several land data assimilation instances that are enabled based on LIS around the world, with users ranging from different domestic and international agencies to academic users at several universities around the world. So LIS is a community software and has benefited significantly from investments by NASA and partner agencies. And LIS is, for example, is used operationally by the US Air Force for their global land characterization needs related to, again, numerical weather prediction, transboundary water management, and so on. So let's get into the details of the software and the capabilities. The LIS modeling suite consists of three components. It has a pre-processing environment called LDT, or Land Data Toolkit, which is used to develop the pre-processing inputs that the modeling system needs. So for example, LDT handles the development of the modeling domain, processing of static parameters such as land cover, soils, topography that LIS needs, and all the other pre-processing needs related to data assimilation. The modeling system LIS is in the middle here and has a ton of capabilities encompassing many different land surface and hydrology models, support for meteorological and remote sensing data sets, and tools for data assimilation, and so on. And finally, at the back end, we have another environment called the Land Surface Verification Toolkit, or LVT, that enables the routine evaluation of land surface outputs from LIS. So LVT includes the support for a large suite of land surface reference data products from ground and satellite and other model products. So LVT can also develop derived products from the land surface model outputs. For example, it can be used to develop anomalies and percentiles of land surface outputs from LIS, which are often used to as measures of drought characterization. So there are two main web pages for the LIS project. The lis.gsfc.nasa.gov, which you see on the left, is the main page where you can find information about the project, links to research publications and news stories, and so on. We also have a page on GitHub where you can get access to the code, documentation, example test cases. There's also a discussion page here on GitHub where you can find archives of questions from the user community and post your own questions about the use of LIS. So LIS is an open source software, and using the GitHub page, you can also contribute to the software development. Most of the LIS code is written in Fortran and a bit of C. For parallel computing support, we use a message passing interface or MPI. There are lots of external software libraries that LIS relies on. One of them, a primary one, is called the Earth System Modeling Framework, which is a library for building and coupling Earth system models. LIS also require libraries such as NetCDF, GRIB, HDF, GeoTIFF, mainly to enable the direct use of remote sensing datasets natively without having to reformat or reprocess the datasets. So this schematic here shows how exactly LIS works. The core of the system consists of an ensemble of land surface models, and the user can select which ones to use. And these models all require inputs of land surface parameters such as land cover, soils, and vegetation, topography, and so on. And these are processed by LDT. And these models also require information on the atmospheric boundary condition, such as air temperature, incoming radiation, and precipitation, and so on. And these land models then solve the governing equations of the soil, vegetation, and snowpack medium, and then predict estimates of land surface fluxes and states such as evaporation, runoff, and soil moisture, snowpack, etc. So now we have observations of many of these land surface states from remote sensing. And this is where the data assimilation subsystem in LIS come in. And we're using the data assimilation subsystem. We can use these remote sensing observations to constrain the land surface model states. And similarly, LIS has an inverse modeling system that allows us to use the observational information to refine the representation of model parameters. As I said before, LIS has also been coupled to many other Earth system models. So when LIS is coupled to the weather research and forecasting model, for example, so LIS acts as the land surface component and uses the atmospheric boundary condition from the atmospheric model. So the idea of having this uncoupled mode when it's decoupled from the atmosphere is that in the uncoupled environment, we can study and improve the land surface processes and isolation before employing them in a fully coupled Earth system model. A bit of word about the software architecture. LIS is designed as an object-oriented environment with a 3-layer structure. The top driver layer, LIS, has functionalities for supporting generic modeling features such as configuration, time management, etc. LIS also has a middle layer called abstractions layer, in which we have generic representations for key functionalities in LIS. So for example, there is a land surface model abstraction that can be extended for implementing new land surface models. So in fact, all the models that are incorporated in LIS follow this structure. And similarly, by extending the relevant abstraction, other functionalities for including new data assimilation schemes, meteorological data sets, remote sensing data sets, they can all be developed. So this flexible structure essentially allows the incremental development of software without having to overhaul the entire system when new things are being added. So one of the important capabilities in LIS is for data assimilation. And using this flexible software architecture that I described, support for a ton of remote sensing measurements of various land surface variables from many different sensors have been developed within LIS, as shown here. And there's also been a ton of scientific papers written over the years that describes these capabilities for assimilating soil moisture, snow conditions, vegetation, land surface temperature, water storage, both separately as well as concurrently. So land surface, as we know, is pretty unique. The heterogeneity on the land surface is tremendous, particularly compared to other Earth system components. In addition, we all know that the direct impact of human is more ubiquitous on the land surface. So as humans, we have modified the land tremendously by building reservoirs and pumping water out of the rivers and aquifers for irrigation, and so through disturbances such as deforestation and fires. So having observations about these impacts is absolutely critical for the accurate characterization of the land surface processes. In that sense, the land data assimilation capabilities is a very critical capability. So again, land surface models, strictly speaking, provide the water balance calculations at a grid scale. So we need a separate class of models called hydrological models to take this information and to develop estimates of water storage and flow in the river channels. So the LIS environment includes a number of hydrological models that enable these capabilities. So this figure on the top right here shows an example of the global hydrological simulation done with LIS, where you can see all the major river basins around the world. So now getting to the drought side, now how do we use all this information for drought characterization? Typically, we think of drought as a situation when there is a prolonged period of dry conditions leading to a shortage of water, right? So shown in this schematic from Chagnon et al., Chagnon in 1987. So this is typically caused by an increased atmospheric demand or an absence of rainfall or precipitation. And based on how severe these driving factors are, the dry conditions can take hold on the land surface state. So for example, when you have a significant period with little rain, the dry conditions will manifest in the soil moisture state, which can then subsequently bleed into deficits in stream flow and perhaps in groundwater. So typically there are different types of droughts that are defined based on the variable of interest. So precipitation-based characterizations are usually called meteorological drought, whereas agricultural droughts are defined based on soil moisture or groundwater deficits, and hydrological droughts are defined based on stream flow deficits. Because each of these variables have very different timescales of memory and evolution and could provide different aspects to characterizing drought. So for example, in the more recently in California, when the atmospheric river events occurred, there were wet and flooding conditions on the land surface, whereas the groundwater was still dry and depleted. So on the surface, you would think the drought is over, whereas in reality, it's not, if depending on which variable you're looking at. So we should also remember that anthropogenic processes have a huge influence in the development and propagation of droughts. So human abstractions from rivers and aquifers for agriculture has a big impact on how the droughts develop and how severe they are and how long they last. So therefore, incorporating remote sensing inputs through data assimilation to account for these factors is hugely important for drought characterization. So I'll show a couple of examples in a second from our own research. So yeah, how exactly do you measure drought? So the typical approach is to examine the time series of a given variable like soil moisture at a location, and then examine the conditions that are abnormally drier than the average condition. So you can define different levels of severity based on how far the deviations at a particular time are from the normal. So in fact, the US Drought Monitor defines a 5-level drought categorization based on a percentile setup. So when the soil moisture percentiles are below 30, it's considered the beginning of drought, for example. So similarly, when the percentiles are below 20, then you're considered to be in a moderate drought situation, and so on. So the most severe category is when soil moisture percentiles are below 2, or in other words, conditions that only occur 2% of the time. So now let's look at a couple of examples of drought characterization from LIS modeling and data assimilation. So this is an example where we assimilated remotely sent soil moisture data within a land surface model to examine how soil moisture characterization is improved. So in this particular example from for July 2018. The left plot here shows the US drought monitor based characterization. And the middle panel shows the land surface model based drought estimate when no assimilation is conducted. And on the right panel shows the drought estimate with soil moisture data assimilation. So you can see that the drought estimation is improved, particularly in this southern region and encompassing Texas. The time series also shows a similar comparison. In this plot, we are looking at the percent of area under drought in this southern region. The black line shows the estimate from US Drought Monitor. The model estimate without assimilation is in green, and then the estimate with data assimilation is in red. So you can see that the assimilation, the red line, gets closer to the black line, or the sort of the quote-unquote observation of the US Drought Monitor. Another example where we assimilate the terrestrial water storage measurements from NASA's GRACE mission. Again, on the left, you can see the US Drought Monitor example for two cases, one in 2011 and one in 2012. And in the middle panel shows the land model-based drought estimate when no remote sensing data infusion is done. And then on the right, the revised drought estimate when after we incorporate information from GRACE. So the middle panel shows that the drought estimate is underestimated. And when GRACE data is introduced, it improves the representation of the moisture conditions, and it produces drought estimates closer to what the US Drought Monitor reported. Moving on to another example of assimilating, this time, vegetation conditions. So in this case, we assimilated leaf area index measurements from remote sensing. So these panels here show improvements in evapotranspiration compared to 4 different reference data sets as a result of assimilating LAI. So in these plots, just to help you out, the warm colors or the reddish colors indicate places where assimilation provides improvements, and the cool colors are places where assimilation leads to a reduced level of agreement with the reference data. So overall, ET is improved as a result of LAI assimilation pretty much everywhere. And you can also see some areas where larger levels of improvements are seen. So these areas, such as the Corn Belt, the lower Mississippi, the Central California region, they all correspond to places where there is significant agricultural activity. So essentially, the assimilation or the remote sensing infusion is helping to characterize the impact of changes in ET from human activities like agriculture. So sure enough, this also leads to an improvement in characterizing droughts. So here, this plot here is a map of improvements in the correlation of drought intensity relative to the US Drought Monitor. So again, the warm colors indicate that the agreement with the US Drought Monitor is getting better with the data assimilation of LAI. We see that, again, assimilation is beneficial in improving drought estimates, with stronger improvements over the areas in the central US here. And these patterns also match up well with areas where there is significant irrigation activities happening, as shown in the right here. So essentially here, the assimilation of LAI helped to capture the changes in vegetation seasonality because of human activities like irrigation, and that ends up improving our representation of extremes such as drought. So hopefully I provided a quick run through of LIS and how the land modeling and data assimilation is essential for developing accurate representation of drought situation. So LIS is a complex software with more than 1.5 million of lines of code. So though LIS has been ported on many systems, it still can be a non-trivial process to install it on your own environment. So more recently, the LIS team helped to develop a containerized version of LIS to improve the ease of use. So this containerized version is available as an app image container, and it's available on our GitHub page. So we have been thinking about how to enhance our capabilities for drought monitoring, improving upon environments like the NLDAS. So NLDAS is a very widely used also for drought applications in the US, but it's also limited to continental US. It doesn't include any data assimilation. So NASA, Goddard, and Marshall have been partnering to leverage capabilities in LIS to develop sort of the next generation NLDAS-like environment by covering all of North America and by enabling all our multivariate data assimilation capabilities and running the system at a much finer scale. We are targeting a 1 kilometer resolution scale. Many of you who use NLDAS also know that it's starting to have some issues with this meteorology. And the NASA team has developed an experimental product that leverages NASA's remote sensing and modeling capabilities, including the GPM iMerge datasets, reanalysis like META2 and GeoSci-IT, and working with our partners in Canada and bringing in their Canadian precipitation analysis. So the vision is to employ this environment routinely at NASA SPoRT for enabling high resolution and routine drought characterization and building on the LIS-based capabilities that exist at SPoRT. So to summarize, LIS is a software that has pioneered a lot of different land data assimilation environments around the world for characterization of both land surface conditions and hydrological extremes like drought. And I hope a few examples towards explaining this. So the capabilities in LIS for remote sensing and data infusion through assimilation are critical. And for exploiting the information we have available from a vast array of remote sensing measurements. And that is necessary for developing better representation of the land surface heterogeneity and impacts of human management. So with that, I'll stop, and thanks for listening.
Thank you, Sujay, for the comprehensive overview of NASA's Land Information System. We will now go to Jonathan Case to provide an overview of SPoRT-LIS soil moisture analyses for enhanced drought situational awareness. Jonathan, over to you.
Welcome to session 1B of the application of NASA SPoRT Land Information System Soil Moisture Data for Drought ARSET course. I'm Jonathan Case of the NASA Short-Term Prediction Research and Transition Center, or SPoRT, and I manage the SPoRT configuration of the LIS, which I'll describe in this presentation. I'm also a contractor for the NASA SPoRT Center with ENSCO Incorporated. The outline of topics for this presentation include the motivation behind configuring an instance of LIS here at the NASA SPoRT Center, a description of the climatology and real-time setup of the SPoRT-LIS, details on the components of the 3-kilometer resolution LIS, a discussion of placing soil moisture analyses into historical context using percentiles, and comparing and validating SPoRT-LIS soil moisture percentiles to the US Drought Monitor weekly product. The early motivation for SPoRT-LIS was to improve regional weather prediction models by generating enhanced land surface initializations using the LIS framework. Our early publications demonstrated improvements to surface temperature, moisture, and precipitation forecasts. We also showed the utility of incorporating satellite-based vegetation observations into LIS in place of climatological representations of vegetation. The applications of LIS at SPoRT evolved into enhancing a forecaster's situational awareness for a variety of forecast challenges, such as thunderstorm initiation at the National Weather Service Birmingham, drought analysis, and applying soil moisture fields to understanding areas of heightened flooding threats. These efforts led to SPoRT expanding to a full contiguous United States domain, or CONUS, as well as targeted international applications for the NASA Severe Program, OCONUS regions. Let's begin with a high-level diagram of the SPoRT-LIS process. The 3-kilometer resolution SPoRT-LIS is an observations-driven land surface model run driven by meteorological analysis inputs or forcings. At the core of the SPoRT-LIS is the NOAA land surface model, as you see in the middle diagram. The LIS framework takes in a variety of static fields projected onto the model grid that are used by the NOAA land surface model. Outputs of SPoRT's instance of LIS include derived fields such as soil moisture percentiles, reformatted data for various interfaces, and custom delivery methods. We also have a parallel version of the SPoRT-LIS that assimilates soil moisture active, passive, or SMAP satellite observations of soil moisture since the SMAP mission began in April 2015. But the majority of this presentation will be discussing the SPoRT-LIS without data assimilation. So a little bit about the NOAA land surface model. At the core of SPoRT-LIS is the NOAA model, which is driven by observational analyses. The NOAA land surface model is the same parameterization scheme as run in operational US prediction models such as the NAM, GFS, or GEFS. The model represents complex physical processes of the soil vegetation snowpack state. And the NOAA model has 4 standard layers at depths of 0 to 10, 10 to 40, 40 to 100, and 100 to 200 centimeters below ground. And NOAA solves physical equations to obtain updates to the soil moisture, soil temperature, snow, and heat and moisture transport between the model layers and back into the atmosphere. Let's take the next few slides to look at the input static and time varying fields that go into the SPoRT-LIS simulation. Soil properties are represented by the state's soil geographic or StatsGo database. StatsGo consists of 19 unique soil classes representing sand, silt, clay composition and the accompanying physical properties defined in lookup tables. Worth noting is that in the SPoRT-LIS, the soil characteristics are uniform in the entire vertical column at every grid point. The land use or vegetation inputs come from the 20-class International Geosphere Biosphere Program database, which is based on NASA MODIS satellite observations. As with the soil classes, lookup tables define many of the physical properties of how the vegetated surface interacts with incoming radiation and extract water from the soils at various rooting depths. Other static inputs required by the LIS include topography, which is important to downscale coarser resolution meteorological inputs to the higher resolution LIS grid. Maximum snow albedo in the upper right represents the reflectance of snow-covered surfaces, especially freshly fallen snow, which will have the highest albedo or reflectance. And the bottom center is a soil temperature bottom boundary condition applied to the 100 to 200 centimeter lowest layer as a bottom soil temperature climatology. As alluded to earlier, one of the unique contributions to the SPoRT-LIS is the incorporation of real-time satellite-derived green vegetation fraction, or GVF. GVF is defined as the percent coverage of healthy, actively transpiring vegetation. It partitions incoming energy into sensible, latent, and ground heat fluxes, which determines surface heating, evaporation into the atmosphere, and warming of the soil layers. Traditionally, a monthly climatology has been used in models to represent the seasonality of vegetation coverage. And shown at right here is a monthly climatology representing the green vegetation fraction for the month of May. And a limitation with this method is that vegetation is always represented the same way from year to year and season to season. So this might not accurately reflect vegetation response during an anomalous weather or climate episode such as drought or delayed or early green ups in the spring months. Therefore, since September 2012, SPoRT has been incorporating real-time satellite vegetation derived from the VIIRS instrument. The NOAA-NSDAS organization produces daily updated VIIRS Green Vegetation Fraction over the entire globe at 4-kilometer resolution, comparable to the SPoRT-LIS's 3-kilometer grid resolution. And at the right, you can see is a daily averaged VIIRS GVF during the month of May 2013, when a delayed green up occurred across much of the continental US. And if we look at the difference between the monthly average VIIRS GVF input and the climatology GVF, it's quite apparent that during May 2013, there's much lower GVF in the VIIRS product across much of the upper Midwest and the eastern US, given by the dark brown shades. This delayed green up occurred during spring 2013 because there were predominance of well below normal temperatures, especially over the northern plains, the Midwest, and extending into the southeast US. So situations like spring 2013 can significantly alter the soil moisture solution, as below normal vegetation leads to decreased evapotranspiration and more moist soils as a result. In contrast, an early green up, which occurred in spring of 2012, can cause enhanced evapotranspiration and enhanced soil drying during anomalously warm early spring periods. So let's shift gears now to talk about an overview of the SPoRT-LIS simulation in terms of the historical spin-up, climatology, and the real-time components. So the SPoRT-LIS timeline consists of a multi-decadal spin-up run where the soil states respond to time-varying input atmospheric forcing over a long period of time. This provides a sufficiently long period for the soils to reach an equilibrium state with the input meteorology. Using outputs from the long duration spin-up, we then reran the historical period to develop the climatology period spanning 1981 to 2013. And the climatology run is then extended to real time, and it's continuously cycled every 6 hours to produce routine outputs at an hourly output frequency in real time. There is also an experimental forecast component to the SPoRT-LIS, extending out to 2-week forecasts with every 6-hour cycle of the LIS. The spin-up in the 1981 to 2013 climatology of SPoRT-LIS is driven exclusively by the North American Land Data Assimilation System Phase 2, or NLDAS-2. NLDAS-2 consists of hourly analyses at about 14-kilometer resolution, and it's managed by the Environmental Modeling Center in real time. Satellite rain gauges and radar observations contribute to the observational-based analyses of NLDAS-2. Since NLDAS-2 has about a 4-day latency in real time, we bridge the gap between the historical to T-minus 4-day time period to real time using the Global Data Assimilation System, or GDAS analyses, and that bridges minus 4 days to the present time with each cycle. And this bridges the gap between NLDAS-2 latency and the current time. And by continuously cycling, we are always producing analyses with no more than 2 to 8 hours latency at any given moment. Additionally, 1-kilometer high-resolution hourly precipitation estimates are incorporated from the multi-radar, multi-sensor, or MRMS product. The MRMS is replacing the precipitation rates from the GDAS analyses in that T-minus 4 days present. The high-resolution MRMS product also builds in detailed short-term precipitation information into the analyses, which can be important during active precipitation episodes. So the SPoRT-LIS run goes back 5 days for each cycle and subsequently overwrites outputs as new NLDAS-2 analyses become available. This ensures that the long-term solution of SPoRT-LIS is consistent with the NLDAS-2 driven climatology database. SPoRT-LIS also includes the experimental 2-week forecast of soil fields driven by the US's Global Forecast System, or GFS model. These forecasts can provide outlooks of potential rapid drying episodes or drought relief that can be very important for pre-planning and response activities. The next few slides show sample output variables from the SPoRT-LIS web viewer. On this slide is the 0 to 10 centimeter volumetric soil moisture, or VSM, which is defined as the fraction of water volume per total soil volume. And for visualization purposes, we scale this by a factor of 100. The theoretical maximum as defined in the soil lookup table is just under 0.5 or 50 in the visualization image here for clay type soils that have high porosity or lots of small pores taking up the spaces in the soil volume. Meanwhile, sandy soils with coarse spaces have fewer spaces between the granules of sand and thus have a lower soil water holding capacity volumetrically. So in the 0 to 10 centimeter volumetric soil moisture image at right, the black contours indicate areas of active precipitation in the previous hour. And the VSM often closely follows the pattern of soil type due to the defined water holding properties of each soil classification. The relative soil moisture, or RSM, is the ratio of the current volumetric soil moisture between the defined wilting and saturation values for a given soil classification. Urban and water points are masked and show as white shading in this plot. And urban points are masked because the NOAA land surface model defines a very narrow dynamic range between the wilting and saturation points, and therefore responds overly fast to wetting and drying periods. The image at right shows the 0 to 100 centimeter deep RSM with very low % saturation values over the high plains, as outlined in the black oval here. Meanwhile, high values of RSM nearing saturation are found across the California Sierras, the Rockies, in the western US, and over southeast Canada. Many of these areas are very moist because of melting snow at this time. So this slide shows a comparison of how the RSM at different NOAA soil layers responds to incoming precipitation. The top 0 to 10 centimeter layer RSM in the upper left responds almost instantly to incoming rainfall or the lack thereof. One can see that the soils quickly moisten from rainfall, but subsequently dry after the rainfall ends in this top layer. The drying can be due to infiltration of water into lower model layers and or evaporation back into the atmosphere. The 10 to 40 centimeter layer in the upper right also responds fairly quickly to rainfall in a matter of hours, but with a bit more delay in the moistening and drying compared to the top 0 to 10 centimeter layer. Meanwhile, the deepest two layers behave quite differently, with a longer delay in moistening of the 40 to 100 centimeter layer from heavy rainfall. It can take days to weeks or longer for the 40 to 100 centimeter layer to respond to incoming rainfall or the lack of rainfall. And finally, the 100 to 200 centimeter layer in the lower right has a barely perceptible response to this 2 to 3 day rainfall event. It can take months to even years for the deep soil layer to reach a balance with the input meteorology, especially during long-term drying episodes. To help SPoRT-LIS users understand soil moisture changes over various time frames, we also produce temporal change fields in the total column 0 to 200 centimeter RSM. The 1 to 2 week changes align with the US Drought Monitor weekly update frequency and help to capture short-term changes in soil moisture. In this example, drying occurs in the 2 weeks leading up to May 1st, 2023 along the West Coast, Midwest, and the Northeast US. A moistening trend is found over the California Sierras, Rockies, and Northern Plains, and that's largely due to the snowmelt infiltrating into the top soil layers. The 2 week to 1 month time changes in the total column RSM help to target episodes of flash drought or drought relief. In the image here, we have a 1 month change showing a drying signal occurring during the month of April 2023 across the West Coast and Arizona, as the heavy winter precipitation ended during April, and that resulted in a significant soil drying compared to the month of March. Moistening signals, meanwhile, are occurring over southeast Texas and from eastern Florida up to the middle Atlantic region. A snowmelt signal is again prevalent across the mountains of the west, southern Canada, and the northern plains. The 3 to 6 month time changes in the total column 0 to 200 centimeter RSM target seasonal soil moisture changes. In this example, the 6 month drying since October 2022 is confined to Florida and the Southwest, but there's large areas of substantial moistening that occur over much of the higher elevation of the western U.S. due to the prolific rain and snow season they had this past winter. And then in the upper Midwest due to snow melt and then substantial precipitation that moistened the soil from East Texas into the Northeast United States. The annual change map is able to provide users with year-over-year change to compare current soil conditions to a year ago. Compared to 1 year ago on May 1st, we see a corridor of drying that extends from the northern high plains southeastward into northern Florida, with focused areas of moistening compared to a year ago seen over the northern high plains, the upper Midwest, eastern Texas, and the Intermountain West, and also the middle Atlantic area. So while soil moisture and its changes are useful by themselves, placing the values into historical and climatological context are quite valuable to increase situational awareness. We have therefore constructed daily soil moisture climatologies spanning 1981 to 2013. Initially, we developed these climatological distributions for each county of the lower 48 states of the United States. In the example shown here, we have a frequency distribution of the 0 to 200 centimeter full column RSM for Madison County, Alabama for the 29th of November. All of the LIS-NOAA grid points that reside within Madison County are grouped together for each output day of the 1981 to 2013 climatology period. And in the chart above, we see that the 0 to 200 centimeter RSM binned value of 55% has occurred about 350 times in Madison County during that 33-year climatology period. So by seeing where the current soil moisture values lie within the county's historical distribution, we come up with ranked percentiles at each grid point to create maps of the percentiles as shown in the upper right. We then apply the drought community standards for relating the ranked percentiles to drought categories, and the definitions are as follows. Soil moisture less than or equal to the 30th percentile is considered D0 or unusually dry. Soil moisture less than or equal to the 20th percentile is D1 or moderate drought. Soil moisture less than or equal to the 10th percentile is D2 or severe drought. Less than or equal to the 5th percentile is D3 or extreme drought. And less than or equal to the 2nd percentile is D4 or exceptional drought. And these percentile standards are not only applied to soil moisture here, but to numerous other inputs and indicators that go into the various inputs that the U.S. Drought Monitor weighs in on their weekly products. Also worth noting is that that vertical dash line is the county average mean value of the 0 to 200 centimeter relative soil moisture, and that's for Madison County, Alabama for the actual day of 29 November 2016. And in this example, you can see that the county average value is way on the dry side of the tail of the distribution here. So in this slide, we demonstrate anomalously dry soil moisture over Madison County, Alabama, and Sevier County, Tennessee for the 28th of November, 2016, which is the day of the Gatlinburg, Tennessee deadly wildfire event. So to describe in a little more detail these histogram diagrams, the gray bars represent the distribution of the 1981 to 2013 climatological soil moisture values for the 28th of November. The vertical colored bars are the reference percentile thresholds that are defined for the drought thresholds on the left dry side of the distribution, as well as the mirrored wet thresholds on the right side of the distribution. The vertical dashed line, as I described earlier, is the present day county average values of 0 to 200 centimeter relative soil moisture. And in this case, it's for November 28, 2016. And the corresponding 0 to 200 centimeter relative soil moisture values for the reference percentiles, as well as the county average value, is listed in the table at the upper right of these charts. So now if we animate the daily histograms for Madison County on the upper left and Sevier County in the upper right during the year of 2016, we see that there's a dramatic transition from anomalously moist conditions early in the year to exceptionally dry conditions by mid to late autumn, which was what led up to the Gatlinburg wildfire event in Sevier County, Tennessee. If you keep an eye on the vertical dash line, you'll see how the county average RSM values are changing from day to day during 2016, with an initial decline during the spring months. But then as you get into the late summer and autumn months, you can see that vertical dash line really starts declining dramatically to the left, shifting toward anomalously dry values. So if we let that animate a little bit more as we go through the autumn months, you can see the mean average values shifting further and further left onto the dry tail of the distribution compared to the 33-year historical climatology. These soil moisture histograms can also reveal information about weather and climate regimes at a given county and their seasonal behavior. In this slide, we're presenting an animation of soil moisture distributions for Tuolumne County, California on the first of each month, spanning May 2022 to April 2023. This county resides largely in Yosemite National Park in the central Sierra Mountains of California. Notice there's a strong drying trend in the 1981 to 2013 soil moisture distributions during the dry season of months of May to October, while there's a steady moistening trend that occurs from November to April as the rainy season sets in across central California. In these distributions and for Tuolumne County, the wide range of values suggests that both drought and wet years are equally common, given the wide range of historical solutions of soil moisture that occur in this county. So now let's compare Tuolumne County normals to Del Norte County, which is along the coast in far northwestern California. Here we see an even stronger drying trend from May to October during the dry season, but in Del Norte County, California, there's a very rapid moistening in just 2 months from November to January with the onset of the wet season. Another contrast between these two counties is how much tighter the historical soil moisture distribution is in Del Norte County, suggestive of a much more consistent climate regime compared to the central Sierra Nevada mountains further inland. So in addition to the county-based climatologies and percentiles, we also generate grid point-based climatologies and percentiles. These percentiles are generated for all cumulative layers of the volumetric soil moisture, 0 to 10 centimeters, 0 to 40 centimeters, 0 to 100 centimeters, and 0 to 200 centimeters. We apply a 1-week centered moving time window to construct climatology distributions at each grid point and then for each day of the year. Each grid point has a historical sample size of 33 years times 7 days of the moving time window for a total of 231 points at each grid point. Shown at right here is the total column 0 to 200 centimeter percentile for May 1st, 2013 over the Central Plains. So let's compare that now with the grid point based percentile map with the county based percentile map for the same day. And there's several benefits to having the grid point based method, such as a fixed sample size at each point compared to variable sample size for the counties, which have different sizes. And if we toggle back and forth here, we can see that there's a better spatial continuity in the grid point based percentiles here compared to the county based percentiles, which shows a lot of county border edges, which is not evident. It's much smoother field in the grid point based percentiles. Also, urban corridors are not masked in the grid point based percentiles, and it has a full domain coverage outside of CONUS where the counties are confined to within the continental US. And finally, percentiles can be examined for shallow and deeper layers, thus spanning different timescales of measuring soil moisture anomalies. So let's wrap up session 1B with a comparison and validation of the 0 to 200 centimeter relative soil moisture county-based percentile drought categories to the US Drought Monitor official weekly product. This first example compares the SPoRT-LIS drought categories for the Southern Plains during an exceptional drought period from 2011 to 2012. We start with a map comparison of the SPoRT-LIS percentiles in the upper left to the US Drought Monitor map in the bottom center for early August 2010, when conditions were fairly moist over the Southern Plains except for Louisiana. The plot at right shows time series of aerial coverage in drought categories for the SPoRT-LIS in the top row versus the US Drought Monitor in the bottom panel, spanning 2010 to 2012. The vertical dashed line in the time series plots is showing the position of early August 2010, where you can see that there's fairly minimal drought aerial coverage at this time over the Southern Plains. However, if we advance by 1 year, we can see that extreme to exceptional drought has set in across much of the Southern Plains. Summer 2011 featured persistent, extremely hot temperatures with little to no rainfall across much of Texas and Oklahoma. Wichita Falls in northwestern Texas had 100 days with maximum temperatures of 100 Fahrenheit or higher, establishing the hottest summer on record there. At this location in the time series, both the SPoRT-LIS and the US Drought Monitor shows exceptionally high amounts of coverage of extreme and exceptional drought in the 20 to 40% aerial coverage of D4 exceptional drought in the US Drought Monitor product, with a little lower peak in the SPoRT-LIS. If we move forward another year into early August 2012, we see that the drought has shifted northward, more toward the Central Plains. And in fact, large parts of the CONUS experienced an extreme flash drought that began in June 2012. One characteristic worth noting in the time series plot in the upper right is that for this case study period and this region, at least, the SPoRT-LIS appears to have an uptick in the coverage of exceptional drought areas slightly before the official US Drought Monitor product uptick occurs. So this feature suggests that strong dry soil moisture anomaly trends in SPoRT-LIS may help to be a leading indicator of rapid drought onset. This next example revisits the flash drought that led up to the Gatlinburg wildfire in late November 2016. During late August, a modest drought aerial coverage is seen across the southeast US, especially Georgia and eastern Tennessee. However, by late November, the drought dramatically expanded in both coverage and intensity due to a combination of well above normal temperatures and virtually no rainfall from September through most of November 2016. The SPoRT-LIS does have greater aerial coverage of D4 drought than the US Drought Monitor product, but the ramp upward in all drought categories trends very closely with the US Drought Monitor, and again may slightly precede the uptick in the drought categories in official US Drought Monitor classifications. So finally, let's close out with a validation of the 0 to 200 centimeter relative soil moisture drought categories against the whole period of record of the US Drought Monitor from year 2000 to 2022. We validated SPoRT-LIS county-based percentile drought categories in all the regions of the CONUS shown here, and we examined the bias and of the drought aerial coverage, as well as how well the aerial coverage correlated with the Drought Monitor weekly product. So let's look at the statistics here on this slide, which shows the bias in the table at left and the correlation coefficient in the table at right. So a bias of 0 represents an unbiased aerial coverage, and a correlation of 1 would be a perfect correspondence between the two products. So here we see the best overall validation statistics occur over the Southeast US, Southern Plains, and the Northern Plains regions. A combination of low aerial coverage bias and high correlation occurs in most of the drought categories. The Southeast US in particular has the best overall validation, with a correlation coefficient above 0.7 out to the D4 drought category. And that suggests that soil moisture deficit is an important component to the US Drought Monitor assessments over the Southeast. Meanwhile, we see that the SPoRT-LIS percentiles tend to overrepresent drought coverage in Florida, the Northeast US, and the Midwest, given the larger positive biases indicated here. And in the Southwest US, the SPoRT-LIS percentiles generally underrepresent the drought coverage, suggesting that soil moisture deficits don't play much of an important role in, or as important of a role in determining drought categorization in the Southwestern US. So in summary, SPoRT has designed its own configuration of the land information system over the continental US at around 3-kilometer resolution. Coined the SPoRT-LIS, it provides historical and real-time outputs of land surface variables with a primary focus on soil moisture and accompanying percentiles to contribute to informed decisions on drought categorization. The SPoRT-LIS drought categorization based on deficits in soil moisture percentiles verifies best against the official US Drought Monitor weekly product in the central and southeastern US. Future endeavors include conducting a similar validation of drought categories using the cumulative layered soil moisture gridded percentile product. And we're also teaming up with the Goddard Space Flight Center for an expanded and improved land data assimilation system that will cover all of North America at 1-kilometer resolution. It'll be run in the cloud, and it will serve as a replacement to the SPoRT-LIS. We will also expand upon the experimental forecast soil moisture states and percentiles by producing ensemble and probabilistic outlooks of soil moisture changes, which could help to improve short-term outlooks of flash drought scenarios. So I'd like to thank you for your time and attention, and I hope this session has been informative and valuable to those who are interested in this. Thank you very much.
Thank you, Jonathan, for the terrific overview of SPoRT-LIS. To summarize some of the things that we've learned today, the NASA Land Information System, or LIS, provides a framework for the comprehensive characterization of the land surface and hydrological extremes, such as drought. The capability of remote sensing data infusion through data assimilation enables the representation of land surface heterogeneity and human management impacts. SPoRT-LIS provides real-time surface fields and soil moisture percentiles for informed decisions on drought. Looking ahead to next week, in order to reinforce what we learned today and to prepare you for part 2, we've prepared a micro lesson which you can find on the training page. The micro lesson will allow you to independently practice the knowledge and skills from today's webinar. We hope that you will complete this before week 2 so that you'll be better prepared for the future parts. In next week, part 2 will extend the concepts covered today to focus on early and established applications of LIS for drought analysis in operations. As stated earlier, there will be one homework assignment for all 3 parts of the training. Answers must be submitted via Google Form, which can be accessed from the training page on the ARSET website. Homework will be made available on May 31st with a due date of June 14th. A certificate of completion will be awarded to those who attend all live webinars and complete the homework assignment by the deadline. You will receive a certificate approximately 2 months after the completion of the course. Below is the contact information for today's trainers, along with links to the SPoRT webpage, ARSET website, and social media. If you enjoyed today's webinar, we hope you will sign up on the ARSET listserv to receive notifications of future trainings. And please follow us on Twitter and YouTube. We will now transition to the question and answer portion of today's training. And thank you so much to everybody who has been submitting your questions. We do encourage questions, not only today, but throughout the entirety of this 3-part webinar series. So big thanks to everybody that has been sending them in. So to jump right into it, given the limited amount of time that we have left, question number 1, is SPoRT data available in every part of the world? And whoever answered that, feel free to unmute and answer. Okay, well, I guess we'll answer. NASA SPoRT data are publicly available, and SPoRT-LIS data availability will be addressed in the 3rd session of this webinar series. SPoRT-LIS is currently only valid over the continental United States, but there are many other applications of LIS internationally, including on the continent of Africa, as well as South Central and Southeast Asia, etc. So we hope that you'll join us for part 3. We'll be able to learn a lot more about SPoRT availability. Question number 2, how can we process a sequence of multi-satellites, for example, Sentinel-2 multispectral instrument, to analyze the trend of which parameter for 20 years? And it looks like there's a second part to this question. To study the evolution of land cover for approximately 30 years, which parameter should we use, and how can we analyze the sequence of satellite imagery for this period of 30 years? I will give any of the trainers a moment if they wanted to unmute and attempt to answer these questions. The first part to me is a little unclear. It says multi-sequence of multi-satellites for 20 years. Well, Sentinel-2, first Sentinel, Sentinel-2A was launched in 2015, so it's probably not going to give you that time series that you're after, that 20 years. But there are different ways of using multi-satellites for different applications. A lot of ARSET trainings have covered that. So it really depends on what parameter that you're looking to monitor or to observe. And so maybe if you wanted to rephrase your question and answer or ask it again, we might be able to address that. The second part says to study the evolution of land cover for approximately 30 years, which parameter should we use, and how can we analyze the sequence of satellite imagery for this period of 30 years? If you're looking for a 30-year time series, the best bet is probably going to go with the different Landsat missions because they give continuity for over 50 years of land cover and land change. So I would address that. There's different ways of using multispectral data to assign pixels, different land cover categories. They're based on both statistical approaches as well as machine learning approaches. We do have ARSET trainings that are focused just on this application. So whoever asked this question, I hope that you would go to the ARSET website and find that training that specifically deals with this application. But if we didn't answer it if your question was not answered, please do feel free to ask it again and we'll try to address it in the limited time we have. So question number 3, how can we, yes, please.
This is Kevin Buell at SPoRT, and I have Jonathan Case with me. I'm afraid Jonathan's audio wasn't going so well in his office. Could he address the question 1 at this point really quickly?
Absolutely, Jonathan. Yeah, I'm glad your microphone is now working. Please do unmute and feel free.
Yeah, so in terms of sport data being available in every part of the world, I think it's a two-part question here. One is that sport data in general are publicly available, and we'll be addressing that in some of the session 3 presentations. But right now, the SPoRT-LIS solution itself is valid over the continental United States, but there are many other applications of the LIS internationally: Africa, Southeast, South Central Asia, the SALDAS, the Famine Land Data Assimilation, FuseNet. Certainly, Sujay Kumar could even address some of those other applications internationally.
Yeah, thanks, John. So LIS is used for many land data assimilation system instances. The global land data assimilation system called GDAS, which is run at Goddard at a 25-kilometer grid scale, uses LIS. And there are the FuseNet effort that John mentioned also runs LIS on a global configuration, as well as higher resolution configurations over Central Asia and Africa. And there are, again, researchy components to similar LDAS instances using LIS over the Middle East and North Africa, and over India, over South America, and so on. So many of them are, done by the individual organizations in those countries or in those regions. So feel free to contact us and we can provide you more details.
Terrific. Thank you, Sujay and Jonathan. Question number 3, how can we integrate the idea of land surface temperature estimation with the factors that lead to drought? Can I say that land surface temperature has a direct impact on drought? And whoever answered that, feel free to unmute.
Hi, yes, this is Richard Hain, NOAA's National Centers for Environmental Information. Drought is basically an imbalance between water supply and water demand. And really, water supply is precipitation. So if you have a lack of precipitation or less precipitation than is normal for an area, you have a tendency towards drought to develop. And water demand in nature is evapotranspiration. So the hotter the temperatures, the more evapotranspiration. And abnormally high temperatures can increase evapotranspiration, and it generally tends to exacerbate existing drought conditions. But drought is largely initiated by a result of reduced water supply or a lack of precipitation. There is one thing that is really becoming more of a research interest in recent years, and that is flash drought, where hot temperatures coupled with lack of precipitation can result in the rapid development of drought. So temperatures are important, but the main thing is lack of precipitation.
Richard, thank you so much. Yeah, please go ahead.
John, I have something to add to that too. Can you hear me?
We sure can.
Yeah, so this is Chris Hain from NASA Sport. So while it doesn't really, Richard's answer was really good about talking about how the connection between temperature and drought can be considered. We do use land surface temperature as a metric for monitoring conditions of drought. Through the relationship between evapotranspiration and changes in land surface temperature and some energy balance approaches, we can use land surface temperature to actually tell if vegetation is stressed. So there's a couple of products that use land surface temperature as a drought indicator. But as Richard said, the actual physical connection between land surface temperature and drought is more of one related to water. And obviously a lack of water will lead to elevated land surface temperatures. And that's kind of the connection that we can see from space when we can tell that vegetation is stressed or something like a flash drought might be developing. So while there's not a direct connection with the actual drought, we can actually use land surface temperature to give us some more information about how water stress and vegetation stress is evolving in the land surface.
Great, thank you so much, both Chris and Richard. I think we have time for one last question. So question number 4, what are the key components or steps involved in the process of data assimilation? How how do different data assimilation methods such as the common filtering or variational assimilation work?
Yeah, Sean, this is Sujay. I can try to answer that. So very simply put, at a very high level, data assimilation is the process where you sort of do a weighting between your model predictions and your observational inputs. So if you trust your observations more, then you nudge your system more towards the observations. Or if you don't trust your observations, you stick with the model, right? So as a crude analogy is what we sometimes use is called the sleepy driver scenario, where let's say you're driving on the road and you're feeling sleepy, and then every few seconds you open your eyes and then correct your your path, right? So having that opening the eyes is sort of analogous to having those infrequent observations, and you correct your behavior. That's essentially the idea. So the most important thing in the art of doing data assimilation is knowledge of errors. How much do you trust your observations, and how much do you trust your model? And so specifying those errors is how is one of the most important inputs for data assimilation. And there are lots of assimilation methods out there. As the question alludes to, Kalman filtering and variational methods are some of the common approaches, and there are mathematical forms in which they provide an update after incorporating observations are different. So variational methods typically they solve some sort of objective function, minimizing the errors, and then come up with the updated state. The filter is also essentially similar, but the approach typically is sequential. That you every time you get the observation, you provide an updated model state, and it's typically based on estimating the minimum variance in the difference between the model and your observations. So I hope that helps.
Great, thank you so much, Sujay. I do want to respect the time. I do see that we're a little over. So first and foremost, I want to thank everybody, all the participants for joining, wherever you're joining from. Thank you for taking out this last hour and a half to learn about SPoRT-LIS and how it can be applied for soil moisture estimates. So, and also I want to thank all of our guest trainers today, Chris Hain, Sujay Kumar, and Jonathan Case. Thank you for the wonderful presentations that you gave. And I also want to thank all of the SPoRT team that might not be maybe presented today, but that we're working in the background to help make this a successful first part of this 3-part training. I also want to acknowledge the ARSET team who's also been working in the background to make this successful as well. We do want to remind everybody the micro lesson is available on the training page, so do please access that, start working on it, and we hope that you will have that completed before next Wednesday, the second part of this webinar series. It will not be graded, but it will help prepare you for all the material that's going to be covered over the next 2 weeks. So please do go to the ARSET training page, access that, and we hope to see everybody back here in 1 week's time for the second part of this webinar series. So stay safe, and we hope to see you soon. Thanks.